I'm Ilkay Yildiz. I'm a PhD student at Northeastern University, and I have been a summer intern in the computer vision team, Styleworks stream. So today I will talk about learning from comparisons. So you may be familiar with classification in the machine learning setting, which is a very common setting. So in this setting, each sample in the dataset has a corresponding class label, and the machine learning algorithm tries to find that specific class label. So if we were to give an example from the Styleworks stream, we have a room image, and an expert is asked which style that image is, and she may say it is modern. So also in many other domains, especially recommender systems, experts can provide comparison labels. So in this setting, the expert is given with a pair of samples, and she actually indicates the relative order of the samples. So let's say in the style domain, we have a pair of room images, and the expert may say the first one is more modern than the other one. So why would we even use those comparison labels when we have class labels? So first of all, comparison labels are more informative than class labels. So with class labels, we can assign each sample to a single class, but we can only learn inter-class relationships. With comparison labels, we can actually order the samples even within the same class. And also, it has been shown in many domains, and especially in recommender systems, that humans are better and they agree more when they are making relative judgments, such as comparing two room images. And rather than when they are making absolute judgments, like when they are assigning each room to a single class. So that is why, as you can imagine, if we were to train a machine learning algorithm on such more informative and less noisy comparison labels, then we would get a lot better predictions. So that is why in the Styleworks stream, we benefit from such comparison labels. So the dataset that we have consists of room images, and each room image actually receives style labels from 10 different experts. And as you may imagine, since style is a very subjective object, we have high inter-expert variability in the style labels. So that is why we do not use the class labels, which are very noisy, but instead we generate comparisons from class labels. So what a comparison indicates exactly is that we compare the number of labels that the pair of images have, and that indicates the comparison outcome. So after generating comparisons, we train a Siamese neural network. So in a Siamese neural network, we actually have two identical base neural networks. So let's say the neural network is a function f. So each base neural network actually receives a room image, then predicts the corresponding style spectrum. Then, to actually predict the comparison label from the style spectrums, we look at the difference of them, and this indicates the comparison outcome. And to predict the comparison, we actually look at the sign of the output. So how do we actually train this neural network? We do not use standard similarity loss functions, which is typical for Siamese networks. Instead, we actually use the so-called variability comparison model. So this model assumes that for each sample in the dataset, we have an underlying score, which is positive and scalar. And if we were to know all the scores of all samples, we can actually predict both class labels and comparison labels. So let's say the score is abbreviated as S, and we have images I and J, and the corresponding scores are Si and Sj. And the model is a probabilistic model on comparisons, and it says that the probability of image I beating image J in a comparison is in this formula. How do we actually tie these scores to the setting of Siamese networks that we have? We actually reparameterize each score as the output of the base network, which is style spectrum. So more specifically, let's say the images are indicated by the feature vectors xi and xj. Then actually, the score becomes e to power f xi, so which is the base network output. Then we actually do this reparameterization. The probability of I beating j in the comparison becomes 1 over 1 plus e to power fxj minus fxi. So as you may remember from classical machine learning, this is actually a logistic function of the difference between the base network outputs, fxj and fxi. So this actually means that we can train the neural network by maximizing the likelihood of such logistic outcomes. So that's actually what we do. And after training, why do we use this Siamese network for? The final aim is to be able to predict the style spectrum of images, because we want to be able to understand the style of the customer, and based on that, we want to make recommendations. So on the test set, at the inference time, if we're given a room image, we can extract the style spectrum. Then we search for the nearest neighbors of the style spectra and recommend the corresponding images, which are style aware. So thank you for listening. Come back for more explainer videos.